Cryo-electron microscopy is a form of TEM where samples are studied at cryogenic temperatures. Recent advancements in the technique have allowed for almost atomic resolution of samples not altered in any way, making it increasingly popular for structural biology. It has been used to image single particles of bacterial enzymes, mitochondria, viruses, and ion channels. Biological samples naturally shrink and collapse in a vacuum as the water contained inside boils off at the low pressures. In order to preserve some of the native structure of these delicate samples, they are dried or stained, both of which introduce artifacts into the images. To combat the shrinkage and collapse, biological samples are flash frozen in a process called vitrification. Ice crystals can damage samples due to expansion and the edges of sharp crystals. Even when the ice fails to cause significant damage, ice strongly diffracts electrons and obfuscates signals from the sample. Vitrification is the process by which a liquid is frozen without forming a crystalline solid. These solids behave similar to polymers, where there is a change in viscosity over time rather than an abrupt phase change. While water can be frozen amorphously at a cooling rate of megakelvins per second, it is simpler to add cryoprotectants. Cryoprotectants decrease the freezing temperature to prevent ice formation and increase the viscosity of the solution. Along with rapid cooling, this allows biological samples to be protected and supported by the amorphous solid. The cryoprotectant of choice for cryo-TEM is liquid ethane. After samples have been vitrified, they can be placed in a TEM the same way as other samples, as long as they are maintained at liquid nitrogen temperatures. A focused beam of electrons is transmitted through the sample, with the transmitted beam being collected for bright field images and the diffracted beams chosen for dark field images. However, most biological samples are extremely radiosensitive and can only be imaged at low energies. These low-dose beams generate low signal-to-noise. However, recent developments in technology have finally allowed the technique to achieve near-atomic resolution of less than 4 angstroms. The most important of these is the Direct Electron Detector Device, or DDD, camera. While previously electrons were converted by scintillators to photons in order to form an image, the DDD cameras allow electrons to be translated directly into an image. The result is dramatically better resolution, signal-to-noise ratio, and sensitivity. Increases in computer power allows for these images to be further refined, resulting in reliable 3D density maps of single particles. Cryo-electron microscopy has proven an advantageous technique that has elaborated upon a number of medical problems. It helped image the structure of the herpes virus capsid, revealing atomic-level details for the first time during research done on the human cytomegalovirus, which is responsible for birth defects, organ transplant infections, and AIDS deaths. The researchers explained that their structure should inform rational design of countermeasures against human cytomegalovirus, other herpes viruses, and even HIV/AIDS.